Hello, hello. I wanted to talk about my most recent project that I've been working on. Basically, I had the idea of combining a genetic algorithm using a convolutional neural network's softmax scores, which is the scores that it uses to assign probabilities for each of the classifications, as the fitness function in a genetic algorithm. So I'll kind of go into it. So just to recap on how genetic algorithms work, um, you have a fitness function, and then you have a population, which is initialized originally randomly. So that's what G1 is. And as you can see, G1 here has a fitness of 0.005, so really low. And in each generation, you take some of the fitter individuals and use them to repopulate the second generation. So you can see generation 2 has a fitness function of 0.007, so it went up a little bit. Repeat this over many generations, and I showed here that on generation 99 we reached 85%, or a fitness score of 0.85. So you'll improve over time. That's basically how this works until you eventually converge somewhere. So it got me wondering. I actually woke up in the middle of the night one day and had this idea. What if you use the softmax output of a convolutional neural network as the fitness function? So softmax basically returns scores for each of the possible classes, and the scores add up to 1. And as such, you can interpret the softmax scores for each of the classes as probabilities. And convolutional neural networks are good for image recognition. So basically, why do you do this to me? All right. So basically, the idea here would be um, that you could evolve images that had very high softmax classifications, and as such, the images should look like images of that class. So you could evolve new images of things based on a neural network's abstract understanding of what that thing looks like. So that's pretty neat. So basically, this is what that would look like. You have the genetic algorithm repeating over generations, and this time, though, it's hitting the convolutional neural network and using the softmax score, so it's trying to evolve an image which gets classified as, yes, this image we're evolving is very much, XYZ, a dog, a cat, whatever you've trained your neural network on. And so here's the big question. So I used the MNIST dataset, or CNN trained on the MNIST dataset, or parts of it for this project. The big question is, will this produce an image which is human recognizable, like the one on the left, or will it produce noise, like the image on the right? All right, so let's find out. And here's some results that I got. These images on the top row all had very high softmax scores, so very, very confident classifications, and all of these are supposed to look like the image for a handwritten digit of a 1. So they should ideally look like what we have down here at the bottom. So these images, when I passed them through the CNN, had like 99.9% softmax scores. And as you can see, the scores up here are nearly as high a lot of the times, but it just looks like junk. It looks like noise. Look at this one all the way on the right, 99.989% softmax score. So it's very confident that this is an image of a 1, and it's just a little white dot on a black background. So that's pretty goofy. So what's going on here? Basically, CNNs are good at classifying human recognizable images, but the reverse isn't true. Humans aren't good at classifying CNN recognizable images to a high degree of confidence. And basically, what this means is there is a space of all images that a CNN will classify with a high degree of confidence. And this includes the human recognizable handwritten images, in my case, but they're a minority. It also includes a ton of other images that to us just look like junk, are not human recognizable at all. So basically, the reason for this is classifications are made by extracting differentiating features between your two classes. And therefore, we're really going to end up just evolving images that have those differentiating features, that highlight the differentiating features in the CNN between two or more classes that we trained on. And a differentiating feature is, first off, it's different from the image of the thing itself, and it's also abstracted from our human understanding. So this is why, unfortunately, I was unable to evolve a image of a 1, because what ended up happening is the genetic algorithm evolved images of the specific little pixel configurations that differentiated the images of 1s from images of the other class. And exactly the logic behind, those results are just abstracted from human understanding, because that's kind of just the nature of neural networks. There isn't a logical step-by-step spelled out process for under the hood, what's going on under the hood. It's kind of hidden from us. So unfortunately, this method could not be used to evolve images. Sad face. I was really excited to try this out. I thought it was like a really neat experiment, but it didn't end up working out. But if you're interested in seeing my code that I used for this project, it is on my GitHub, and the link is in the description. So thanks a lot, and I'll see you later. Bye-bye.